Have you ever wondered what happens to advanced composites like glass fiber and carbon fiber when exposed to extreme freezing temperatures like -50, or even down to -250 degrees Celsius? Do they crack, lose strength, or stay strong as ever? Today let's break it down. Break it. When we talk about composites, we're really talking about two parts: the fiber reinforcement, either glass or carbon, and the polymer matrix that binds everything together. The fiber provides strength and stiffness, while the matrix transfers load and gives shape. But here's the catch: polymers and fibers respond very differently to extreme cold. Let's start with glass fiber reinforced composites, GFRP. Fibers. Glass fibers themselves are amorphous and relatively stable even at cryogenic temperatures. They don't become brittle easily. Matrix. The polymer matrix, often epoxy, is more sensitive. At -50 degrees Celsius it becomes stiff and brittle because polymers approach their glass transition temperature, Tg. Below Tg, mobility of polymer chains reduces, making the material less tough. So, what happens overall? The composite's stiffness increases, but its impact resistance and toughness decrease. Micro-cracking between the fiber and matrix can occur because they contract differently when cooled. Now let's talk about carbon fiber reinforced composites, CFRP. Fibers. Carbon fibers are crystalline, stable, and perform exceptionally well at low temperatures. They don't lose strength or stiffness, even at -250 degrees Celsius. Matrix. Again, the polymer matrix is the weak link, but compared to glass fiber systems, carbon fibers have better thermal compatibility with resins, so the mismatch in contraction is less severe. So overall, carbon fiber composites tend to retain strength and stiffness better at freezing temperatures than glass fiber composites. They still face reduced toughness, but they resist cracking and embrittlement more effectively. Why does this matter? At temperatures between -50 degrees Celsius to -250 degrees Celsius, like in aerospace, satellites, cryogenic storage tanks, or polar conditions, GFRPs are cheaper, but they suffer more from matrix cracking and toughness loss. CFRPs are more reliable in these conditions, which is why they're used in spacecraft and liquid hydrogen tanks. To summarize, glass fiber composites. Stable fibers, but the polymer matrix gets brittle. Higher risk of microcracks at cryogenic temperatures. Carbon fiber composites. Fibers remain very strong and stiff. Matrix still hardens but with better fiber matrix compatibility, so overall performance is superior. That's why in extreme cold environments, carbon fiber is the go-to material. So next time you see a rocket, a satellite, or even advanced racing cars, remember, the reason they often rely on carbon fiber is not just about weight, but also how they behave in extreme cold.